This is the video for the physics recitation for October 25th. We'll start with Chapter 9, question 24, which the question is: a flywheel with radius 0.3 meters starts from rest and accelerates with a constant angular acceleration of 0.6 radians per second squared. Compute the magnitude of the tangential acceleration, the radial acceleration, and the resultant acceleration of a point on its rim, A at the start, B after it is turned through 60 degrees, and C after it is turned through 120 degrees. So first we have the diagram, right? Acceleration going that way, a tangential acceleration this way, radial acceleration is going towards the middle, remember that. So A, the radial acceleration is r times w squared, which, since it starts at rest, then w is 0, so that equals 0. The tangential acceleration is r times angular acceleration, so radius times angular acceleration. You know, you write out the components that they've given you here. Here you can just plug it in, and you'll get 0.180 meters per second squared. And because both of these are constant, these components are constant, then this is going to be the tangential acceleration for all points, all times within this problem. So it's constant. And then the acceleration, we see up here, acceleration equals the square root of the tangential acceleration squared plus the radial acceleration squared. So that's just going to be the same here as tangent, because radial acceleration is 0. So yeah. B, after it is turned through 60 degrees. So first we're going to start with this equation here, and all of the pink equations are given in your formula sheet. I didn't see this one specifically there, but all of the rest should be there. So that one you just have to memorize. So here, the initial angular speed, 0, of course, because we already established that. And then you'll find that w equals 2 angular acceleration times the difference in angle. We take the difference in angle, times it by 2 pi radians over 360, and that gives you the number of radians that we're working with. And so you just kind of put that in there. So then you end up with w equals square root of 2 times angular acceleration times the w that we calculated equals 1.12 radians per second. Then you can insert that into the radial acceleration equation, r times w squared. We have r times w squared equals 0.378 meters per second. That should be squared. Yeah. And then remember that this is the tangential acceleration, so you put that in here using this equation up here, down here, and you've got the acceleration is 0.18 squared plus 0.378 squared equals 0.419 meters per second squared. And then moving on to part 3, C. So then we do the same thing that we did up here. We've got 120 degrees times 2 pi radian over 360 degrees equals this many radians. Then we, do the same thing that we did here, just kind of rearranging the equation square root of 2 r radians that it's turned through equals this many 1.58 radians per second. Then the radial acceleration, same equation, r times w squared equals 0.752 meters per second squared. And the acceleration equals both the tangential and the radial acceleration, each of them squared and then summed, and the square root of that. And that gives you 0.774 meters per second squared. So that's all for question 24 on 9. If you have any questions on any of these problems, feel free to email me, and I'll do my best to explain them. Moving on to question 40, still within chapter 9. The question is, a light string is wrapped around the outer rim of a solid uniform cylinder of diameter 75.0 centimeters. So remember, we usually work with radius, and we usually work with meters. So then we would need to convert that if we use that later on. That can rotate without friction about an angle through its center. A 3 kilogram stone is tied to the free end of the string as shown in the figure. So if you look at the question, then it has a better figure than this, but I did my best to draw it here. When the system is released from rest, you determine that the stone reaches a speed of 3.50 meters per second after having fallen 2.5 meters. What is the mass of the cylinder? So we're going to work with work in this. So we, write out our work equation. We know that there's no initial kinetic energy because it's at rest. The potential energy, it does have that, and we'll consider this line here where the stone has dropped 2.5 meters. We're going to say that that's the ground, in quotation marks. So then you'll just kind of use the 2.5 as the height, and we'll go through that later. The work other, there's no friction, so there's none of that. There technically could be other types of work other, but there's none here. The final kinetic friction, there is some. And there's some for the rock, and there's some for the stone. So it's the sum of that this component is going to be. And since we're taking this to be the ground, there's no potential final energy. So we see that in the end, the potential initial equals the kinetic final. We know that the potential initial is just the potential energy of the stone. And then once it drops, then the stone has kinetic energy, but also the cylinder has kinetic energy because it's turning, because there's still motion that's going and causing it to turn. So you see that here, stone plus cylinder. So here, mass times gravity times, the change in y equals the kinetic friction of the stone plus the kinetic friction of the cylinder. So we see that, sorry, I think this continues on. Yeah, it does. Okay. So right, kinetic friction of the stone, pretty simple. Same thing we've been working with, 1/2 mv squared, and that would be the final, v final, plus 1/2 the inertia times the angular speed final, right? Because W initial is 0 because it starts at rest. Right, and so here's just the components written out, but we already know that. So then we'll move on to the next section, next page. So then, right, potential energy here equals 1/2 mv squared. That's what this means. Plus 1/2 of, right, and then this one is the inertia kind of equation. So over here we see that the inertia for a solid cylinder is 1/2 big M R squared. So big M is the cylinder, right, and little m is the stone, right? And then V equals R times W, right? That'll come in just a second here. Right, so here you've got 1/2 I, right? So I, and then that should be W squared. But then if you take, here it says V final over R all squared, right? So this one, if you take W, you just move the R underneath here. And that gives you V over R equals W. So you just square that whole thing, right? And then you see that there is R, and then if you move this squared to each part, then it's R squared on bottom, R squared on top, so you can cross those out. And this whole thing, or these two sections, give you 1/2 mv squared plus 1/4 big M v squared. Right. And then at that point you will isolate M, because that is the question that it asked us. What's the mass of the cylinder? And so you'll have mg delta change in y here. Then move this side over here by minusing it on both sides over here, and then you times this whole side by 4, which is where this one comes in, and that one gets crossed out, and then divide this whole left side by V final squared here, and then you'll get M. So it's just rearranging the equation, right? And then you plug in all those numbers, and the number that you get is 18.0 kilograms. So moving on to question 44 of chapter 9. A bicycle racer is going down the hill at 11.0 meters per second. So V initial, this one. When, to his horror, one of his 2.25 kilograms wheels comes off when he is 75 meters above the ground. So height is 75 meters above the ground, above the foot of the hill, sorry. We can model the wheel as a thin-walled cylinder, 85 centimeters in diameter. So, right, convert that to meters and to radius. You've got that. And ignore the small mass of the spokes. How fast is the wheel moving when it reaches the foot of the hill if it is rolled without slipping all the way down? Right, that's question A. And then B is, how much total kinetic energy does the wheel have when it reaches the bottom of the hill? So A, we're also going to be using the work equation here. And we've got no slipping. Okay, so here. Initial kinetic energy. Now remember, this is a circle that's rolling, so it has both the kinetic energy that's linear, and which is 1/2 mv squared, and it has the kinetic energy that is rotational, which is 1/2 inertia times W squared. Right, and so we've got that kind of equation right here. And then it does have potential energy because it's up here. There's height. There's no work other. Right, so there's no work other. So we can just ignore that. And then there is a kinetic final energy because it is still moving at the bottom of the hill. But no potential energy at the bottom of the hill because height equals 0 there. Right, so then We know that inertia equals mr squared from the formula sheet, and that v equals rw, and so we'll just kind of put those in there. So A, it's asking us for how fast the wheel is moving, right, when it reaches the foot of the hill. So it's asking for v final right here. So we've got 1/2 mv squared plus initial. Should be a 0 because it's initial. Initial plus 1/2 inertia, we just move that in there, times w, we rearrange this, put that in just like we did before, squared, and that gives you 1/2 mv squared plus 1/2 mv squared, right? So in the end, you get mass times just, 1 whole mv squared. So then putting that into this equation here, we've got 1/2, sorry, not 1/2, mv squared plus potential energy, mgh, equals kinetic final energy. Now again, we have moving rotational kinetic energy, and we have linear kinetic energy, so it's also going to be 1/2, not 1/2, it's also going to be 1 whole mv squared. And then you see m is in all of them, so we cross that out. Yippee! And then just take the square root of this whole side, right? So you've got square root v initial squared plus gh equals v. Plug that in, you get this answer right here. And then move on to b. Right, so this is just the final velocity. B, how much total kinetic energy does the wheel have when it reaches the bottom of the hill, right? So remember that this is kind of the kinetic energy formula here. It's just mv squared. That's the kinetic energy total for a rotating and moving wheel or circle or cylinder. Right, so kinetic friction, final kinetic energy equals mv final squared. Plug those in, and this is your answer. So, moving on to question 9 of chapter 10. It's better if you can see if you can look at the problem, because this diagram is not the greatest, but I did my best. So, a grindstone in the shape of a solid disc with diameter 0.520 meters, right, so that's diameter, we'll need to transfer that to radius, and a mass of 50 kilograms is rotating at 850 revolutions per minute. Now initially, you should see this and think, oh, revolutions per minute. Unless the question is asking for revolutions per minute, you typically always change it to radians per second. Right, so that would go over here, revolutions per minute times 1 minute over 60 seconds times 2 pi radians over 1 revolution. This is, if you're taking chemistry, then dimensional analysis. If you're curious about that and haven't learned that, then email me and I can explain that to you. But yeah, so that gives you 89.0 radians per second. Back to the question. You press an axe against the rim with a normal force of 160 newtons, right? So normal force is 160 newtons. And the grindstone comes to rest in 7.5 seconds. Find the coefficient, this one, of kinetic friction between the axe and the grindstone. There's negligible friction in the bearings. Right, so it comes to rest, which means that the W speed final, angular speed final, is 0. Right, it's always good to write out what we've got. And this time we're going to be working with torque. So we know that the normal force times the mu sub F, the coefficient of kinetic friction, yes, is the kinetic kind of force here. So that's just something to remember. Here, there's the diagram. So the normal force is going this way. Diagram. Yippee. Okay. So we've got the torque that's going from the cylinder, and that's going counterclockwise in this case, and that's going to be inertia times the angular acceleration. And then we've got the opposing torque that the axe is causing, and that's the frictional force times the radius, right? So the frictional force times the radius. Yep, and that's going in the opposite direction in order to slow down the cylinder to rest in 7.5 seconds, right? So we've got inertia equals 1/2 mr squared, and then we will, I think that comes in later. Yeah, that comes in later. And then here we've got the speed equation, which we know that the final is 0, so we can cross that part out. The initial angular speed is this one here, right? And we've already calculated that to be 89.0 radians per second, plus the angular acceleration that, and then times the time. So then we're calculating the angular acceleration so that we can plug it in here, right? So we're essentially trying to set these equal to each other, but we don't have the individual components. We'll use this one to get I inertia, and we're using this to figure out the angular acceleration here. So just kind of rearrange this, move the t on bottom after you move this one over here, and then angular acceleration equals negative 11.9 radians per second squared. Then we've got, sum of t equals I curly a equals, right, the inertia thing that I just said, times angular acceleration equals, right, the other one, the force of the torque caused by the axe, right, equals that. So then you plug all of that in, and then you remember, you separate the force of kinetic friction into the components, which is the normal force, 160, times mu sub f, which is what we want. Just kind of move that over there, and you'll get 0.483 equals mu sub f. And so that's the equation, the answer, sorry. So here it's just kind of setting the torques equal to each other and then rearranging stuff, reworking the equations. Next, and I believe this is the final question, yes, is 11 from chapter 10. A 2.00 kilogram stone is tied to a thin, light wire wrapped around the outer edge of the uniform 10 kilogram cylindrical pulley shown here. Right, so it's not solid though. That's why there's a hole here. The inner diameter of the pulley is 60 centimeters. So the diameter is 0.6 meters, which means the radius is 0.3 meters here. So radius 1, the inner one. While the outer diameter is 1 meter, so that's going to be radius 2 is 0.5 meters. The system is released from rest, and there's no friction at the angle of the pulley. Find A, the acceleration of the stone, B, the tension in the wire, and C, the angular acceleration of the pulley. So A, the acceleration of the stone. So we see kind of from the the pulley's point of view, tension is going down. From the rock's point of view, the tension is going up. So we can kind of use that through the sum of F equals ma and say that the mass times gravity minus the tension equals the mass times acceleration, right? We kind of worked on this at the beginning of the semester, and that's the blocks side. And then remember that the sum of the torques equals the inertia times acceleration, and that's also going to equal the tension, right? The tension going this way times the radius, and this would be the total radius from the axle, right? So that would be R2 here. And so we'll just kind of be using these two sections here. And remember that angular acceleration equals the acceleration linear over the radius. So here we reorganize both sides to put t on one side. So we've got mg minus ma equals t. Then on this side we should have inertia times the angular acceleration, but we're putting the acceleration over r here. And then you divide that by r. So that means it'll come out to be r squared on bottom here. And then you can just kind of forget about t and set these two sides equal to each other. And at this point, we're just trying to get the a's on the same side and isolated, right? So we've got an a in here and an a in here. So we'll swap these two positions. So then we have this, take out the a from both of these equations, and we have mg, right? So then we just take mg and divide it by this part after you take out a. And then after you plug in all this stuff, then it comes out to be 2.23 meters per second. Right, and so the inertia you get from over here that I wrote out, I didn't see this on the formula sheet, but it's something that you need to know. Hopefully they'll give it to you in the tests, but I would ask your professor if, for confirmation if you're not wanting to memorize it. All right, so we've got inertia equals 1/2 m, and then r1 squared, so the radius of the hole in the middle of this cylinder, plus r2 squared, so the total radius of the whole cylinder here. And so if you plug in that, you've got 1/2, 10, the mass, it should be a big M here. And then, mass of the cylinder, and this, and that gives you 1.70 kilograms per meter times meter squared, and so that's what you plug in here whenever you plug in all the numbers. Right. So, moving on to the last sections, just a little bit more, then we're done. B, the tension in the wire, right? So remember we had tension equals mg minus ma from the blocks side over here, right here. So we essentially just plug that in and say, the 2 times, right, so you can take out the meters from both sides and say m times g minus a equals 15.1 newtons. Yippee! And then that gives you B. So C is the angular acceleration of the pulley, so curly A equals A over R. That's just in the formula sheet. Equals, right, the acceleration that we just calculated in part A divided by the big radius, right? So this would be radius 2 here, equals this many, 4.46 radians per second squared. So that concludes the recitation video here. I hope that this has explained the questions well, and that please email me if you have any questions. I hope you'll have a wonderful rest of your day. Thank you. Bye.